You can see two pictures up on the board right now that look almost exactly alike. In the first one, you see two media, air and glass. Second one, you see the same two media, but they're reversed. What I want to do is draw a ray that's coming from the air in the first diagram towards the glass. You know that because we're going, in this case, from a low index of refraction to a high index of refraction, n is increasing. What's going to happen to theta? As n goes up, theta goes down, right? So we know that this ray of light is going to bend this way. Theta 2 is going to be smaller than theta 1. Let's try increasing the angle of incidence a little bit here, okay? Let's make the angle of incidence a little bit bigger than it was before. You can see as measured from the normal line, it's about twice as big as it was before. Now, we know that theta 2 here is going to be bigger than theta 2 was with the blue line, but we know that it's going to be smaller than theta 1 still, because as n goes up, theta is going to go down. So it's going to look something like this. Theta 2 bigger than theta 2 was, but theta 2 is still smaller than theta 1. The angle has to decrease because the index of refraction is increasing. Doesn't matter how big we make theta 1, the same thing is going to happen. I can make theta 1 like 80 degrees. When I make theta 1 80 degrees as measured from the normal line, theta 2 is going to be really, really big, but it's still going to be smaller than theta 1 every single time. Now let's take a look at the second diagram here. Almost the same, except this time you're going from glass to air rather than air to glass. This time the index of refraction is decreasing. Let's draw that first ray where we have a theta 1 equal to, I don't know, looks like maybe 35, 40 degrees here. If the index of refraction is going down, then theta will go up, right? So that means theta 2 will be bigger than theta 1 here. Does that make sense? Let's draw another one, this time with a bigger angle of incidence, somewhere around 45 degrees where the green one was in the last diagram. Theta 1 is bigger than it was before. Theta 2 is going to be bigger than it was before, and theta 2 is going to be bigger than theta 1. If n goes down, theta has to go up. You can imagine, if I make the angle of incidence big enough here, that something odd might happen with the angle of refraction. If I make the angle of incidence big enough, then that ray of light refracts so much that it actually skips along the boundary between the glass and the air. This is the beginning of a phenomenon called total internal reflection, where light doesn't refract when it strikes the boundary between two materials. Rather, light reflects when it strikes the boundary between two materials. This angle right here between the normal line and this red ray at which total internal reflection begins to occur is what we call the critical angle. If the angle of incidence is below that critical angle, then refraction takes place as normal. But if the angle of incidence is bigger than that critical angle, then refraction doesn't take place, reflection takes place. This is kind of like skipping a rock in water, right? When you throw a rock, a nice flat rock, straight down to the water from above, it goes into the water. It changes speed, but it goes into the water. Now, if you throw it down at an angle like this, a relatively low angle as measured from the vertical, from the normal line, then it's going to go into the water as well. It changes speed, and it actually changes direction, but it still goes into the water. But if I increase the angle of incidence like this, to have a pretty high angle, like 80, 85 degrees from the vertical line, then you find what happens to that rock sometimes. It skips off of the boundary between the water and the air. That's like total internal reflection. There is one place where that analogy falls apart. Here, you notice that total internal reflection can only happen when you're going from high to low index. It never happens over here. It's never going to happen over here when you're going from low to high, because the angle theta 2, in order for reflection to take place, has to be bigger than theta 1. So in the analogy that I gave you, it would be going from air to water from low to high. It doesn't work that way with light. Okay, light only reflects if it's going from high to low index rather than from low to high. But you can get the idea of increasing the angle from the normal, right? And increasing it to the point where reflection might begin to occur. So what do we define total internal reflection as? It's a phenomenon whereby light reflects off of the boundary rather than refracts. Why does it happen? Well, if we increase the angle of incidence to a great enough degree, my angle of refraction might actually be as big as 90 degrees. Well, if it's 90 degrees, that ray of light can no longer stay in the second material, and it has to start reflecting. So it can only happen, as we said just a minute ago, when you're going from a high index to a low index. Reason being, theta 2 has to be bigger than theta 1. And if you're going from low to high, then theta 2 is going to be smaller than theta 1. So it can only happen when you're going from a high index of refraction to a low index. And of course, the angle of incidence has to be high enough. The angle of incidence has to exceed a value that we call the critical angle, which is the angle of incidence at which reflection begins to occur. Anything above the critical angle, reflection occurs. Anything below the critical angle, refraction occurs as normal, as it did on the worksheet that you were working on a little while ago. We got a picture of a pond up on the board right now. We're going to say that there's a person standing at the edge of the pond right here, and there's a fish in this pond right here. He's happy because he hasn't been caught yet. Now, there's rays of light coming from the sun, millions, billions of rays of light coming from the sun entering this water. Some of those rays of light, probably thousands or millions of those rays of light, will reflect off of the fish. What I want to do is pick one ray of light that's reflecting off of the fish. Let's make it this green one right here. So this ray of light that reflects off of this fish goes at this angle. Remember, this isn't the only one. There's millions of them reflecting at all different angles. We're just picking this one. That strikes the boundary between the water, which, by the way, is an index of refraction of 1.33, and the air, which has an index of refraction of 1.00. There's a normal line right here at which it strikes. You can see that n is going down from 1.33 to 1. N is going down, therefore theta will go up. So theta 1 is right here, theta 2 is right here. Theta 2 is bigger than theta 1 because the index of refraction went down. Is that okay? This is not total internal reflection, right? Not yet. This is just refraction. What I want to illustrate with this diagram, though, is two things. One, this person right now that's standing on the side of the pond will see this fish. But the image of the fish will be different than the fish really appears. The person standing at the pond will not be able to distinguish that this ray of light changed directions when it struck the boundary between the water and the air. This person thinks that this ray of light always traveled in a straight line. So in other words, this person perceives the fish to be back here in a different place than the fish really is. So the person perceives the fish to be shallower than the first fish really is, and further back, further away than the fish really is, because we perceive that ray of light as if it always traveled in a straight line. This is still not reflection. Okay, this is still refraction in the image that we see as a result of this. But what if this person backs up a bit? What if this person on the side of the pond, standing at the edge of the pond, goes back here now? This ray of light that reflected off of this fish still does. Still reflects off of the same angle and still goes up here. But now this ray of light sails right over this person's head. Does this person see it now? No. So the person doesn't see the fish right here. But remember, there were millions of rays of light reflecting off of this fish. There's lots more that the person could see. Let's pick another ray now. Maybe a ray that looks like this. That's more likely to bend into the person's eyes now, right? But notice this angle of incidence for the purple ray right here is bigger than the angle of incidence right here for the green ray. What if the angle of incidence for the purple ray is bigger than the critical angle? This purple ray would then reflect rather than refract. Now what does this person see? The ray of light that was going to refract right into his eyes doesn't refract into his eyes, rather it reflects off of the surface, the boundary between the water and the air. What does this person see now? Top of the pond, nothing inside the pond. You ever notice that? When you stand right up beside a river or a pond, you can see the bottom of it, maybe a log in the bottom or a rock or a golf ball in the bottom, but then you step back from it and at some point you can't see the bottom of the pond anymore? You just see the top? That's because the angle is such that the rays of light coming off the bottom of the pond or the golf ball or the rock or the fish end up reflecting off of the surface rather than refracting. It disappears. It becomes invisible. Where would you need to be in order to see this fish? There is a way to see this fish with this purple ray. Where do you need to be? You got to be right here. As long as you got some kind of air tank, see this fish. If you don't have an air tank or something like that, you're just lying there, probably dead. But if you're alive, you could see this fish. But look, where would you see this fish? You would perceive this fish to be up here, floating in the air, flying? Well, no, it wouldn't be flying because you'd see the fish way up there, but you'd also see the bottom of the pond way up there and the water in the pond way up there as well. So what would happen if you were lying on the kind of the bottom of the pond there, kind of along the side, you would look down here, and you would see the fish in the bottom of the pond. You would look up here, and you would see the fish in the bottom of the pond. So you'd be a little bit confused. You look up, you see the same thing as you look down. And you know that our bodies are made up primarily of water, so we'd be neutrally buoyant. You can imagine a situation where you can't tell which way is up and down based on gravity because you're neutrally buoyant. You look up, you see the same thing as you look down. You can imagine a situation where you could get quite confused as to which way was up and which way was down. If you're a diver, how would you determine which way was up and which way was down? Bubbles, yeah, bubbles always rise, right? You might, by feel, might not be able to tell. By look, you might not be able to tell. But if you breathe out, the bubbles will always go up. So you're going to be able to determine which way is up that way. Is that okay? Let me show you another one. What's this? It's a cross-section of a diamond. Diamonds always should be cut exactly this way as a cross-section. Now, looking at it from above, it doesn't matter whether it's oval or circular or square or rectangle, triangular, but looking at it from the side, it should look exactly like this. Now, don't worry about these numbers, not at all. You buy a diamond, and sometimes they explain four things, 4 C's, 4 properties, the 4 C properties of a diamond. Okay, one of them is color. Normally, you don't want a diamond to have any color. One of them is clarity. You want a diamond to be clear. You don't want it to be foggy because it's not very nice if it's a foggy diamond, right? Carat, that's the size of the diamond. You want it to be big. The bigger, the better, right? And the 4th C is called the cut. We want the cut to be perfect. Cut exactly the right angles, exactly the right values. Why? Because the diamond sparkles more if it's cut at just the right angles. And I'm going to explain to you why that's the case. Looking at this diamond from the side, typically light would enter the diamond from above, right? Diamond on your hand, on your ring finger. Typically, the light's going to enter from above. It doesn't have to, but usually that would be the case. Now, light enters the diamond like this. Goes straight in, let's say. If it goes straight in, it's not going to bend. It is going to slow down dramatically by a factor of 2.4, but it's not going to change direction because it's going straight in. Now, it's going to strike that boundary between the diamond, which has an index of refraction of 2.42, and the air, which has an index of refraction of 1.00. Listen carefully to what I'm about to say. There is no question in your unit test that's about diamonds per se, but what I'm about to tell you translates into other things as well. And there is a question on your test on this. The critical angle between two materials is smaller when the difference in index of refraction is big. We have a really big difference in index of refraction here, from 2.42 to 1.00. That means the critical angle of this diamond will be small. If the difference in index was really, really small, then the critical angle would be big. Got it? Now, because diamond and air have such a big difference in index, the critical angle for diamond/air is small. That means that this ray of light that comes in and strikes the boundary between the diamond and the air is probably bigger than the critical angle. If this was glass, the critical angle is bigger, and this angle might not be bigger than the critical angle. The ray of light would refract. But with diamond, critical angle is smaller. We're probably bigger than the critical angle, which means the ray of light will reflect. Goes over and strikes the boundary between the diamond and the air on the other side. We're probably bigger than the critical angle again. It's going to reflect again. Comes up kind of where it came from. Now, whenever light changes direction, we see it. If it was glass and it refracted out here, that would allow us to see the boundary between the diamond and the air. But it wouldn't cause a sparkle. But when light reflects off of this boundary, we see a sparkle. And then when it reflects again, we see a sparkle. And then the ray comes back up towards where it came from and hits us right smack in the eye again. You see a lot more sparkling when it's reflecting than when it's refracting, right? That's why diamond is, one of the reasons why diamond is a lot more valuable than glass, because it sparkles a lot more. But what about that cut thing? What about that cut thing? Let's draw a diamond a little bit differently here. That's kind of an odd-shaped diamond. It looks more like a carrot than it looks like a diamond, but you got a ray of light coming in here. Oh man, that's way bigger than the critical angle, right? Yeah, light's going to reflect there. You get a sparkle because light reflects there. But now, at this point over here, maybe it's not bigger than the critical angle, and it ends up refracting out the other side. So if the cut is wrong, well, you still see a sparkle. But instead of seeing two sparkles for each of those rays, we see one sparkle for each of those rays. So it doesn't sparkle as much if it's cut poorly, right? Does that make sense? How do you think we determine the critical angle, what the value of the critical angle is? I told you a second ago that the critical angle is small if the difference in index is big. But how do we determine what that critical angle is? Let's do one example to finish off the day, and then we'll pack it up. What's the critical angle for water? By the way, we're assuming air and water here, okay? Air and water. If we want to find the critical angle between air and water, then which way does the light have to be going? From air to water or water to air? Which way is the light going? Air to water or water to air? Water to air. Who said that? Yeah, water to air. In order for reflection to take place, you have to go from high to low index. So if this is water, which has an index of refraction of 1.33, and this is air, which has an index of refraction of 1.00, then reflection might take place. As n goes down, theta goes up. This is my critical angle right here, the angle at which reflection begins to occur. We could call this theta 2 if we wanted. What's the value of theta 2? Anyone? 90 degrees. Let's use a little Snell's law analysis here. Let's say sine theta 1 over sine theta 2 equals n2 over n1. Let's change sine theta 1 into sine theta c, critical angle, over sine 90. By the way, when you're looking for the critical angle, theta 2 will always be 90, always. Equals n2, 1.00, over 1.33. What's sine 90? 1. So this just disappears. Now I've got sine theta c equals 1.00 over 1.33. Let's figure this out on our calculator. To find theta c, we're going to take the inverse sine of 1 over 1.33, and that gives us a value of 48.8. The critical angle, by the way, for diamond in air is something like 24. Like it's way, way smaller. How come? Because there's a much, much bigger gap in index of refraction. Remember, the bigger the difference in index, the smaller the critical angle. This is such a big critical angle because the difference in index isn't that big. I'd like you to finish, please, worksheet number 17 for homework if you haven't done that already.